Because the world is round, it turns me on.
So, what I would now like to address is the weighty question: is slicing the best inventions since the invention of the sliced bread? It's not obvious. In a way, it simplifies the dynamics. It gives us lots of intuition. But the choice of slice is very arbitrary, and we pay a price for it. So here is an example. A totally trivial example. We will slice a two-dimensional plane. So here we are in a plane. This is x1 Cartesian coordinate, x2 Cartesian coordinate, origin. And now we'll assume that we have a SO2 invariance, meaning that all points on a circle of the same radius are physically equivalent. So the circle goes on. And I suppose we start at point x0 in the plane, and we set off with constant velocity v. So what will happen is the particle will move. At the time xt, it will be at this point, and then it will keep going, and the way I've set it up, it's going to be a little hard to draw. It'll come very close to the origin. That can happen. And it's moving with uniform velocity, so it's just going x of t is the initial point x. These are two-dimensional vectors, if you want to write them as vectors, plus a velocity vector, which is assumed time-independent, and the distance covered is velocity times the time. So that's where I'm time t. That's where I'm at this particular time. Now, slicing says, let's take a slice tangent, group tangent vector t prime, and let's just make it 0, 1. So it could be any place. I'll put it in here. So here is the unit vector t prime, and what it defines is defines a slice hyperplane, but as we're in two dimensions, there's just a line. So motion in slice is just, in this simple component, just the first component of the vector. There is no component in the x2 direction. So that's a very simple slice. Now, what does slicing mean? It says that at this point, I can think I'm in polar coordinates, so I'm at the radius r at time t, and I'm angle theta t away by rotation from the point in the slice x t. So this is point in a full state space, which is two-dimensional. This is point in the slice. So I have to compute this angle as I move. Now, what you will notice is that everything is fine until I come close to this origin. So if I plot this angle as a function of time, at this time, this angle is something. Here we are at theta. And as I'm moving down here, it's not changing very much. You know, it's getting a little bit bigger because this line is above. So it's going up someplace. So here I'm at xt, that's this angle. But when I come close to the origin, I'll draw a little blow up. Here is the origin. Here is the line normal to my trajectory. And what will happen is I'll move the same constant velocity here, but the angle will do something totally wild, because it will go all the way over here. So the angle as I come to this time, Tn, T2, this time here, the angle will be it'll go all the way over there. And now as I go away, this angle will do something like that. So what has happened is that as I pass by here in a very short instant of time, that has to do with the distance here. The angle has gone from x2 minus to x plus sometime after, which is roughly what I had before, plus pi, because I've gone almost angle pi around. And if I plot instead of this, if I plot the angular velocity, theta dot, there won't be much change of the angle here, so they'll be small, slightly positive. So this is my time t, this is my time t0, t equals 0, and this is my time t2. T2. What happens is that thing gets very steep, so its derivative is very high, and then it peaks at this point here and goes down. So what has happened is, as we approach this point, as we slightly change our trajectory, this constant velocity trajectory, this will, at this point itself, will go through a delta function, and when we go around, actually the angle will change, even the sign. So we get a very sharp effect, and what has happened? You're going close to the invariant subspace. Now in this case, the invariant subspace, because we're in plane, there is rotation, the invariant subspace is very small. So this is the edge of the slice, which is a point, which is the same thing as the invariant subspace, which you can write as x1, x2 equals 0, 0. In Cartesian coordinates, nothing special, but if you write it in polar coordinates, then r and theta is 0, and this is undefined. So, slicing is not the best invention. And since slice bet, I hope you got it.